Topic B, experiment number 3, cold work and recrystallization. For this experiment, we have 3 different objectives. The first is perform cold work and recrystallization sequence procedures. The second is perform the American Society for Testing Materials grain size analysis. And third, calculate the strength coefficient and strength hardening component using true stress and true strain. After these experiments, you will learn how to cold work affects the hardness and the grain structure of the material, and how the anneal temperature affects the hardness and the grain size of the material. Background: cold work. Strain hardening is a phenomenon by which a ductile metal becomes harder as it is plastically deformed, as the temperature at which the deformation takes place is cold. Related to the melting temperature of the metal, this process is called cold work. This phenomenon can be explained based on the dislocation of the crystallographic structure of the material. When the material gets cold worked, new dislocations form and the average distance between the dislocation decreases. On average, the interaction forces between the dislocations are repulsive. More dislocations tends to hinder the motion of a dislocation by the other dislocations, making the resistance of dislocation motion more pronounced. As a result, the higher defect density causes the material to require more stress to deform. By convention, the degree of plastic deformation by a tensile force, the material as a percentage of cold work, can be expressed as the following equation, where A0 is the initial cross-section area of the sample and A1 is the final cross-section area after the plastic deformation. Recovery, recrystallization, and grain growth. The cold worked sample may revert back to the pre-cold worked state by appropriate heat treatment, or sometimes called annealing treatment. This restoration results from 2 different processes that occur at elevated temperatures: recovery and recrystallization, which may be followed by grain growth as shown in the next figure. In the recovery state, some restored strain energy is relieved by dislocation motion as a result of enhanced atomic diffusion at the elevated temperature. There are some reductions in the number of dislocations. As the temperature goes higher and reaches the recrystallization state, the relative high strain energy of the grain will be released and a new set of strain-free and equax grains will form. These new grains have low dislocation densities and their equiaxial geometries are characteristics of the pre-cold work condition. Now, as the recrystallization is complete, the increase of the temperature will let the strain-free grains continue to grow, and the small grains will gradually diminish, which are consumed by the large grain. As the grains all grow in size, the total area of grain boundary decreases, which will result in the reduction of mechanical stiffness of the material. The mechanical properties at room temperature of a fine-grained metal are usually superior to those of coarse-grained one. To reduce the grain size, the refinement may be accomplished by plastically deforming the material, then subjecting it to a recrystallization heat treatment. Microscopic grain size analysis. Most metals are polycrystalline solids that are composed of a collection of many small crystals or grains with different crystallographic orientations. Fortunately, with optical microscopy, the microstructure of the grains can be studied by observing the differences in reflectivity of the various regions of the microstructure. Just remember that whenever we use the microscope, samples must be prepared before the experiment. So in this case, the sample surface must be ground and polished to a smooth and mirror-like finish. Then the microstructure is revealed by a surface treatment using appropriate chemical reagent in a procedure termed etching. The reactivity of the grains depends on the crystallographic orientations. As a result, in a polycrystalline specimen, vary grain to grain as shown in figure 1. The grain size is often determined when the properties of polycrystalline and single-phase materials are under consideration. It's generally considered that the hardness decreases monotonically with increasing of the grain size. This is because small grains tend to have more grain boundaries, which could behave as obstacles to dislocation motions. We have as an example the figure number 3, where a line with a length of 24 micrometers intersects 5 grains. The actual grain size can be calculated as the next equation, that is L equal to uppercase L over N, where it's equal to the actual length of the line on the image, and N is the number of grains of the line. In this case, just following a simple equation and doing the calculations, the actual grain size can be found as 0.448 micrometers or 0.000189 inches. There is another method to determine the grain size. It is by comparing the number of grains within a standard area, which is divided by the ASTM. The ASTM specifies the grain size number G to represent the number of grains in a 1 inches per 1 inches square on a microscopic image at a magnification of 100x in a function that is shown here, equation number 3, where N is the number of grains in the area that we have described on an image at a magnification of 100. And G is the ASTM grain size number. And there is a specific way to count the number of grains. It's really easy. The grains that do not intersect with any of the box boundaries count each as 1. Those intersect with the boundary count as half. And those located at the corners of the box is a quarter. It's not uncommon that sometimes we have images taken at magnification different than 100x. Then we need to fix our numbers using the equation number 4, where Nm is the number of grains in a 1 per 1 inches box on an image at a magnification other than 100x, and M is the magnification of the current image. The magnification of an image can be determined using the scale bar on the image by the equation number 5, M equal to LP over LS. It's just the relationship, the ratio with the different length of scale. Here we have an example for finding the magnification, where the 10 microns scale bar appears 10 millimeters on the paper. The magnification then is the ratio, and it's equal to 1000. True stress and strain. As shown in figure 5, the engineering stress-strain curve, which usually is obtained from a tensile test, suggests the material becomes weaker after strain passing the maximum point M. This is mostly caused by an experimental artifact. During the development of necking after point M, the cross-section area of the sample reduces rapidly, and so the apparently load capacity of the sample also decreases greatly. In fact, the strain hardening still enhances the strain of the materials as the strain increases. The true stress at any stage of the plastic deformation is expressed as the formula that you know very well, the force over the area. Accordingly, the true strain on that sample is by the finite convention as the equation number 7 that we have here. In terms of the volume, if no volume change occurs, the true strain can be expressed in terms of the diameters of the sample before and after deformation as the equation number 8 that we have here. For some metals, the true alloy, the region of the true stress strain, occur from the one set of the plastic deformation to the point M, where the necking begins, can be approximated by an exponential function. The exponential function is the equation number 9 here. From that equation, to solve for k and n, the first step is to take the logarithm of both sides of the equation number 7 to get the equation number 10. And doing some arrangement, equation 10 can be expressed as the equation 11 here. Then the equation 8 can be considered as a standard linear statistical model. And then we can take as a base the equation 12, it's y equal to b plus 8 times x. And later, substituting instead a, b, and x and y, and in that way we will get the solution. And finally, for the equation of this experiment, using the linear fitting tool in Excel, the value of b and a can be found with the least square error of the data. The strain coefficient k and strain hardening component n can be determined as equation 13 and 14, and that is all.
Experiment steps and procedures.
Step 1. Receive 5 dog bone tensile samples and label them as A to E. Anneal these samples at 700 Celsius for 10 minutes and quench them in water. Measure the dimensions of the cross-section of the samples and nailed hardness values. Fill the table below. Step 2. Perform cold work on each of the samples using the law listed in the table below and measure the cross-section area and cold work hardness values. Use equation 1 to calculate the percentage cold work for each of the samples. Step 3. Use sandsaw to cut sample E to have 5 small cold work pieces. Put them into the furnaces at recrystallization temperature of 250, 355, 400, 555, and 700 Celsius, respectively, for 30 minutes and quench them in water. Mount these pieces and polish them for microscopic investigation. Use equation 225 to calculate the grain size and ASTM grain size number and measure the hardness value for each of the pieces. Step number 4. Calculate the true stress and the true strain using equation 6 and 7. Take the logarithm values and use the linear fitting tool in Excel to calculate the strain coefficient K and hardening component N. Final note: examples of K and N for some alloy materials are shown in the table below.